All right, hello and good afternoon. Um, we are a little bit behind, starting about 5 minutes late, but we're here. So good afternoon. Thank you everybody for hanging in there, waiting patiently. Um, let's see. All right, it So welcome to a very special Chem 400 office hours. This is the Pen Ultimate Edition. Yeah. Raj, hopefully now I'm guessing now you can see and hear. Um, we have an awesome daily mixtape. Daily mixtape today. It is 100% the White Stripes, which is my favorite. Excuse me. My favorite band. If you don't know them, check them out. You probably heard of them. There we go. Doop. But if you haven't, you've got 6 hand selected tracks. From me in the description. And I think this is probably the longest daily mixtape title thus far, at least this year. You can check out Don't Let Them Tell You the Future's Electric. Link in our description. It will kickstart your Friday if it's lagging a little bit. So I can see Vraj is here. I'm here, and I think we're the only 2 humans here. So, oh wait, okay, there we go. So anyways, I don't have any questions. Nobody sent in any through through Canvas or email, so I'm down to talk about whatever you guys want to hear. I've been working on the exam, the take-home exam, and it's actually been more challenging to write this take-home than the last one. I feel like the last take-home exam there was a lot of overlap between subjects and different opportunities to write unique problems that would kind of challenge you guys to think. And this one, things are more straightforward. I've come up with a couple that I think will be good, kind of like, whoa, take a minute, take a step back, think things through type of problems. But it's been more challenging to write. I've got a rough outline. Actually, more than a rough outline. I've got a pretty precise roadmap. I've kind of planned out what topics to cover, what problems to cover. So anyways, I'm starting to kind of bring that together. Once it's complete, I'm going to post a problem breakdown. Normally, I do kind of like that problem breakdown thing where I say, here's the topics, here's the percentage of points in each topic. I do that during the review session, but I'm not going to be doing that for this review session because it literally, our review session ends an hour before the exam opens, so it really won't give you guys much time to prepare at all. So I'll be posting on Canvas the points breakdown, and that way you can be studying over the weekend and figure out what you need help on, And that way you can roll into the review session with your last minute questions. We can get those answered and launch you into a successful exam 3. Okay, Raj, you got a question. So in the multiple choice, will you have a lot of calculation or theory-based questions? Great question. Give me a sec. I have a spreadsheet for that. So let's see, the multiple choice. Where is that thing? Here we go. Okay, so with the multiple choice, I'm looking at the outline now. There's actually no calculation. No calculations involved. The other than like counting your way across the periodic table. So for the multiple choice, you're going to be running into quantum numbers. Yeah. You got quantum numbers. You've got electron configurations. What else? There's VSEPR. Hybridization. And intermolecular forces. So there's like no math. No math involved. So it's literally going to be like for the quantum numbers, I could ask you like to identify the set of quantum numbers that corresponds to, so like this type of stuff. Will be so like identify the set of quantum numbers belonging to like for example an electron in a d orbital on a copper atom. All right. So like then, and you're going to have a bunch of different sets of quantum numbers, and you're going to have to figure out which one belongs to an electron in a d orbital on a copper atom. Let's see. Are the questions more like the textbook or my lectures? Are there any like what is the correct electron config? Yep. Fraj, that is exactly how this one goes. Right? It's either here's an electron configuration, so like He 2s2 2p3, and then it could be A is this carbon, B nitrogen, C etc. Except I do like 5 different choices probably. Or this could also be here's an atom of carbon, is its electron configuration A helium 2s2, 2p, 2b, etc. So, like, both of these are possibilities for electron configurations. So it can go either way with those. I'll either give you an electron configuration and ask you to identify the atom, or I'll give you an atom and ask you to identify the electron configuration. For the oh man. For the VSEPR, hybridization, intermolecular forces, all of these are going to roll out pretty much the same. I will give you a Lewis structure. Give you a Lewis structure. And then I ask you to identify either the hybridization, intermolecular forces, VSEPR geometry, etc. So that is how the multiple choice are going to go down. Quantum numbers, you're identifying the correct set of quantum numbers that correspond to, and I'll give you an electron, an orbital, and an atom. With electron configurations, I give you an atom. You have to identify the correct electron configuration, or I give you an electron configuration, you identify the atom. And then for VSEPR, hybridization, intermolecular forces, I'll give you a Lewis structure and say, what's the hybridization of this molecule? Or what is the bond angle for this molecule? What intermolecular forces are experienced by this molecule? What is the molecular geometry for this molecule? So that is, that's basically how the multiple choice is going to go. Let's see, are there any, like, what is, okay, yeah. Yeah. Totally. So it should be a lot, it should be different, definitely different from the multiple choice for exam 2. It's not calculation based. It's, you know, do you understand what the quantum numbers mean? Do you remember how to do electron configurations? And then do you know your VSEPR geometries, bond angles, intermolecular forces, hybridization? So I'd keep a periodic table handy, and any other reference stuff that you need. And again, I think it's 30 problems long. So same as before. I have a feeling that this multiple choice average, the exam 3 average, will be higher, and that probably the final, which I haven't officially started, will be harder. We'll probably have a lower average. Okay, let's see. More like the examples you did in lecture. For which types? Oh, any. Yeah, I mean, it's all going to be similar to what you've seen in lecture, especially with the multiple choice. The only one that I think will be, that we didn't exactly do in lecture would be the quantum numbers. Excuse me. Because we hadn't really got to electron configurations yet. But the quantum number multiple choice problems appear exactly as I have them written right here. Identify the set of quantum numbers belonging to an electron, and then I'll give you an orbital type and an atom. And then you have to, process of elimination, figure out which set of quantum numbers corresponds. But then, yeah, the electron configurations are going to be very straightforward, like I did in lecture. And especially for the multiple choice, it's all going to be very cut and dry. Because for the VSEPR problems, the hybridization problems, and the intermolecular forces problems on the multiple choice exam, I provide you the Lewis structure. So I give you the Lewis structure of a molecule, and I ask, what's its hybridization? Or what's its bond angle? What's its molecular geometry? So it will be very, very similar to what you've seen me do in class. For this third exam, where you'll see some stuff that I haven't explicitly covered, or some more like thought-provoking, we haven't exactly seen this, will be on the written take-home exam. There should be some challenging stuff. There's even, I'm in the process of writing it, but there's some stuff that I'm going to draw some inspiration, possibly from lab exercise 5. I think there's a couple problems on there that I liked a lot, and we haven't explicitly covered it in lecture, so I think that would be a good candidate to put on the written take-home exam. But I feel like with the multiple choice exam, I want the multiple choice exam to be fairly straightforward, cut and dry, testing for retention of information. And then on the take-home is where I'm planning on pushing the boundary of doing stuff that I haven't explicitly covered in lecture, to see if you can think your way to that point, if that makes sense. Yes, yeah. Okay, great question. You will have the formula sheet for in time for both. Yeah, and Grant, and of course, everything, both the multiple choice and the take home, are open everything. Open book, open internet, open other human, all that jazz. But I know there was with exam 2, due to the delay for the written exam, I believe the Canvas exam opened before I had sent out the written exam. So this time around, you will have them simultaneously. So you'll have a copy of the cover sheet for both. It's not like the Canvas exam will open up and then you'll get the written exam later. You'll have the cover sheet available for both exams for all the time that they're open. So yeah. Also, another thing that you remember how last time I forgot to include extra credit in the written portion of the test. This time the written portion will have the extra credit points built in. So the multiple choice on Canvas will be worth 60, and the written exam will be worth about 70. So you'll be able to score more than what the exam's worth. The exam, all told, is 120 points. Faux show. Totally. Oh, I also, I think, want to put a plug. I know I posted this to Canvas, but oops. But FYI, Raj and I actually had a really good kind of hybridization discussion breakdown. It's kind of like an alternate hybridization convo in the Chem 420 office hours. On Wednesday. All right. And if you are struggling with hybridization or understanding orbital overlap, how bonds are formed, I highly recommend you check it out. I will link in the description. I'll link in the description so you can go hit that up. But if you're struggling with hybridization, it may be you may find that very helpful. I kind of take a slower approach, a different approach to explaining it, and maybe it'll turn some lights on. Okay, Vraj, you've got another question. Let's see. Can I give you an example problem for each topic in the multiple choice, like a multiple choice question? Yeah, I think I can do that. Let me take a look at my master list. Doot. There, let's see. Okay, so yeah, here. So for example, here's a actually, for the quantum number one, let me fire up my periodic table, so it'll be helpful to look at. So for quantum number example, identify the set. Oops. Whoa. The set of quantum numbers that describe an electron in the, let's see, now I gotta pick one, the p orbital of an astatine atom. All right, and these would be our choices. Oops. A, B, C, So let's see, we're going to have principal quantum number for each of these. We're going to have the angular momentum quantum number. For each of them. We'll have m sub L. Then we'll have m sub S. All right, let's see. Then we'll have A, B, C, D, E, F. All right. And yes, my quantum number problems are 6-part multiple choice. Everything else is 5-part, but I always do the quantum with 6. All right, and then we'll have L. And then M sub L. Looks like we're going to have to create some space here. So we've got to fit our M sub S's in. Gonna need to do a little more space rearranging. Then one last shift. All right, now we can write in our the last column of our spin quantum number. All right. Okay, so now that we have all of these columns lined up, let's put some values in here so we can actually do this problem. So, so I'm going to do let me add my numbers in here. Oh, wait, no. And then M sub L's. Okay. So, all right. Now we can do this problem. All right. We can... So, identify the set of quantum numbers that describe an electron in the p orbital of an astatine atom. All right, here's how you go about this. The first major clue that I've given you is the orbital type. All right, in the p orbital. Now, that tells you what your value for L has to be. When L is 0, it's an s orbital. When L is 1, it's a p orbital. When it's 2, it's d. When it's 3, it's f. So automatically, when I tell you that it's a p orbital, you should go and identify all the L equals 1s. All right? Because for every other choice, if L does not equal 1, that is not a viable answer. All right? So instantly, just by knowing what that p orbital means, you've eliminated half of your potential choices for this problem, right? We've gone down from guessing wise 1 in 6 to 1 in 3, dramatically improving our chances. Now, here's where the atom comes in. All right, locate where astatine is on the periodic table. It's down here on the 1, 2, 3, 4th period. All right. Oh shoot, I messed something up. Okay, so I just made this problem up off the top of my head. There's as of right now, there's 2 possible answers to this problem, and I need to correct it. And by the way, on the multiple choice, on the exam, there's only 1 possible answer. You'll never be handed 2. I've already vetted them. I've checked them, so this thing won't occur. I'm going to change 1 number. The number I'm going to change is this one. All right. Okay, so astatine is on the 4th period. Oh, shoot. I need to change a couple numbers. I'm going to change this one to a 5. Actually, all 3 were possible answers. Okay. Astatine's on the 4th period. So when you look at the 3 possible answers right now, F... Oops. What I've changed F to anyway, has its principal quantum number as 5. Not possible for astatine. So on the Canvas exam, will only be 1. There'll only be 1 correct answer. The reason why there are more than 1 possible right here is because I just made these numbers up off the top of my head, and then I didn't go back and check. Whereas for the questions on the exam, I write them and then I double check every answer to make sure that only 1 can be the correct answer. So here, based on the fact that astatine's on the 4th period, yeah, totally. And that's why I switched around some numbers, because that's literally my problem writing process. I'll throw a bunch of numbers in there and then see, okay, which ones are possible answers? I will only want 1, so I changed the rest. F is disqualified because F is a p orbital on the 5th period, and astatine's highest energy p orbital is on the 4th. Now, here's the thing, though. D and B are both still in the running, because here's the thing. Astatine, if it has electrons in its 4p orbital, that means its 3p orbital is already filled. So both of these are possible answers based on N and L, the principal quantum number and angular momentum quantum number. Where we get our tiebreaker here is M sub L. All right. M sub L. M sub L, you'll remember, is defined by L. Its largest possible value is positive L. Its smallest possible value is negative L. And M sub L can never be bigger than L. So M sub L here disqualifies B, whereas you'll notice M sub L for D fits within that bounds, right? It's allowed to be as small as negative L, as large as positive L. So D is the only option who's got the correct orbital, L, has an acceptable energy level, N, and has allowed values for M sub L and M sub S. So we would say that D is the correct answer for this problem. And that is exactly, format-wise, exactly what the quantum number multiple choice will look like on the Canvas test. I'll ask you to identify the set of quantum numbers that describes an electron and I give you an orbital type and I give you an atom. And that's how that works. 2n plus 2. Nope. Oops. Where did that window come from? No, actually. So M sub L can be equal to negative L, 0 to positive L. The 2n plus 2 thing is for saturated hydrocarbons. So I think that might be your MCAT prep. Mudding the Gen Chem waters a little bit. Okay, so that's an example of a quantum numbers problem. Electron configurations are going to be very straightforward. No. There we go. All right. So for electron configuration problems, on the Canvas exam, these come in 2 flavors. All right. They will either... I'll either ask you to identify the electron configuration for an atom. So, for example, I could pick tellurium, and then your options are going to look like A, let's see, 4s2, 3d10, 4p4, or maybe B. We could roll with a Krypton 5s2, oops, 4D10, 5P4. We could also rule AB. What comes next? C. We could do... Oops. Maybe a... Krypton 5S2, 5P4, CD, and we could do who knows? Maybe like HE 2S2, 2P4. And then A, B, C, D, E. How about none of the above? Or none of these? All right. And then what you do is you go, okay, well, where is tellurium? Tellurium is right here. Tellurium's nearest noble gas is krypton. So anything that does not have krypton, I can automatically cross out. That gets rid of two things, right? I can't rule out none of these because both of these things might be wrong. But I know that I've got to have krypton for my noble gas abbreviation. Next, let's look at period. So 1, 2, 3, 4, 5. Tellurium is on the 5th period. And you'll notice that to get from the leftmost end of the periodic table to the rightmost end, or to where tellurium is, we've got to pass through the D block. So I know between our three choices, C doesn't have any 4D electrons. And I know tellurium does, so I can rule out C. So now we have to see, is B correct or is the correct answer none of these? And we know that tellurium has to make it 1, 2 spaces through the 5s block. We got that. It's got to make it 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 spaces through the 4D block. You can do that. And then it has to make it 1, 2, 3, 4 spaces in. And we have 4 electrons in the 5p. So B is indeed the correct answer. All right. So that's one kind of iteration electron configurations can go for. The other way I test for this on the Canvas exam is I ask you to identify the atom with the electron configuration and now I'm going to write an electron configuration. How about this one? The electron configuration xenon six S2 5D 1 2 3 4 5 5D8 4F 14. And again, we've got 5 potential answers. E being none of the above, none of these. A being palladium, iridium, phosphorus, or platinum. All right, and honestly, I find these problems probably a little easier than the previous ones, and that's because we're given the electron configuration, right? So start at xenon. Start at xenon, and then we're going to go 1, 2, 3, 4, 5, 6. You're told to bounce 2 spaces, 1, 2, into the S block, and then we're told to bounce 8 spaces into the D block. Right, so that's 1, 2, 3, 4, 5, 6, 7, 8. So that means correct answer's got to be platinum, because that's 8 spaces in. If you're like, why didn't you use the F block? Well, remember that the F block cuts in here between lanthanum and hafnium, and it is 14 spaces long. So when you move from lanthanum to hafnium, you go 14 spaces through the F block and then pop out the other side of the D block. So for this particular problem, we didn't need to use the F block to solve it. Totally. And I can tell you that half for the electron configurations on the Canvas exam, half of them are here's an atom, find the electron configuration. Half of them are here's the electron configuration, find the atom. So it's a 50-50 mix of those two types of electron configuration problems. All right. So those are electron configurations. Now, we have VSEPR, hybridization, intermolecular forces. All of them left. All right, and so we don't need this periodic table. Let's do that. Now, these ones are all going to be easy. Or not, I shouldn't say easy. These ones are all going to be formatted the same. That's what I meant. When I said easy, I meant easier for me to create, because I could draw one Lewis structure. So, for example, I could draw... let me think. Actually, I gotta pull something up here. Wait, not there. I actually want to pull it up here. There we go. Okay. All right, so for the VSEPR problems, the hybridization, and the intermolecular forces, here's the way they'll go down. So I will give you a Lewis structure. Like the following. Let's get all our lone pairs up in here. And I will ask you to determine and this is where, so for those last problem types, I'll say for the following Lewis structure, determine for example, I could say molecular geometry. Or I could say the bond angle. Or I could say hybridization. Or I could say intermolecular forces. All right. And then I'll give you 5 different options to choose. But really, what you have to do is you have to be able to identify the molecular geometry, bond angle, hybridization, or intermolecular forces. All right? And once you do that, then you find whichever one on the multiple choice is correct, rather than generate 5 different possible answers for this molecule. I'm just going to walk through and identify the molecular geometry, bond angle, hybridization, intermolecular forces, because that's what you'd have to do to solve the problem, and then you obviously checked the correct answer. So one of the things you'll notice about phosphorus is here we have 3 atoms on our central and 1 lone pair, which means we have 4 electron groups. All right, 4 electron groups. Now, whenever you have 4 electron groups, but 3 of them are atoms and 1 is a lone pair, that means that your molecular geometry, well, your electronic geometry is tetrahedral, but when one of them's a lone pair, your molecular geometry is trigonal pyramidal. Trigonal pyramidal geometries have bond angles of 107 degrees. Remember, a pure tetrahedron is 109, but those lone pairs create a greater, have greater repulsion than a bond, so it pinches the angle down by 2. Now, the hybridization comes from the fact that we have 4 electron groups. If we have 4 electron groups around our central atom, we are going to have to use our s and our 3p orbitals all in our hybridization scheme. So this will be sp3. All right. Now, for the intermolecular forces, all right, phosphorus. So we need to look at the difference in electronegativity. All right, and the difference in electronegativity here is chlorine has an electronegativity of 3.5. Yes, Raj, that is correct. One lone pair equals 2 electrons. Yes, okay, yes, and that is also correct. One lone pair reduces the bond angle by 2 degrees. All right, here's the electronegativity difference between chlorine. Chlorine is 3.5. Phosphorus is 2.1. So our difference here in electronegativity is 1.4. That means that we have polar bonds. Ooh, running out of space. Let's try that again. Polar covalent bonds. All right. Now, so polar covalent bonds, but as we learned on Wednesday, just because you have polar bonds doesn't mean you have a polar molecule. All right. If you need polar bonds to have a polar molecule, but if you have polar bonds, you have to ask one more question, and you have to ask, does this molecule have the same group on every position? All right. And here in this molecule, you'll notice that we're tetrahedral. So we have 1, 2, 3, 4 groups around our central atom. And they're not all the same because that fourth group is a lone pair. Dude, ain't nothing wrong with shorthands. That fourth group is a lone pair. And so because we don't have a chlorine in every position, we've got 3 chlorines in one lone pair. That means that this molecule will be polar. So the intermolecular forces here will be London dispersion forces and dipole-dipole forces. Raj, you are correct. We are covering hydrogen bonding on Monday. That is the last intermolecular force. Last intermolecular force we'll talk about. Which is also why I purposefully didn't select an example that had hydrogen bonding here, because we haven't yet talked about it in lecture. It will be on... Whoa. That was loud. It will be on the exam. But yeah, we're not going to cover it till Monday. Let's see. Okay. But there's no... there's no hydrogen, so hydrogen bonding is not a possibility. You got it. Okay, let's see. Hey, you have a question. When you're drawing Lewis structures and you have an atom that can break the octet rule, how do you know to use a bond or a lone pair to use up the electrons? Great question. The answer is it totally depends. All right, it totally depends upon the problem. Because it depends upon the number of atoms you're trying to attach and then completing all their octets. So, for example, so let's look at... So for example, check out perchlorate. All right. When you add up your electrons, chlorine is bringing 7 valence electrons. Oxygen brings 6, but we have 4 of them. So 6 times 4 is 24. And then we have our negative charge, which brings 1 extra 1. So we've got 32 electrons to spend. All right. So chlorine is going to be our central atom. We need to attach all of our oxygens. So that's going to take 2, 4, 6, 8 electrons. We have 24 left to spend. All right. Chlorine right now has a full octet, but our oxygens don't. We actually need to put 6 electrons on each oxygen to satisfy its octet rule. And when we do that, 6 times 4 is 24. So this will spend the remainder of our electrons. So here we've got no electrons left. Then we have to assign formal charges, right? Calculate our formal charges, make sure we have the best resonance structure. If you calculate formal charge for oxygen, when it's neutral, it has 6. In this structure, it has 6 electrons in lone pairs plus 1 bond. So it'll have a formal charge of -1. All of these oxygens have the same formal charge as drawn. And then when you look at chlorine, when chlorine's neutral, it has 7. Here it has 4 bonds and no lone pairs, so 7 minus 4 is a +3. Chlorine has a +3. So we can draw a better resonance structure by taking 3 of our lone pairs on our oxygens and turning them into double bonds, all right? If we do that, it will minimize the formal charge. It'll completely get rid of the formal charge on chlorine and leave only 1 oxygen with a formal negative. So the 3 other oxygens will have 2 lone pairs each and will be double bonded to chlorine. So here's an example where, yep, 3 of the oxygens will be double bonded. Faux show. So this is an example where we have an atom that can break the octet rule, but it's breaking the octet rule by having a lot of bonds, but no lone pairs on there. Let me show you an example where it'll end up having lone pairs. All right, let's take, for example, the polyatomic ion I3 with a charge of -1. Now, iodine has 7 electrons, 7 valence electrons. We've got 3 of them, so this will roll in with 21. Then our charge of -1 brings 1 extra electron to the party, leaving us with 22. All right. Now, iodine is going to be our central atom. We need to attach our other 2 iodines. All right. So this is going to take 2, 4 electrons. Leaving us with 18. Now, the 2 iodines on the terminus, this needs 1, 2, 3, 4, 5, 6, plus 7, 8, 9, 10, 11, 12. All right, and the iodine in the center needs another 4, 13, 14, 15, 16. So to complete everyone's octet, we got to spend 16 electrons. But you'll notice that we've got 2 electrons left. All right. Now, here's the deal. We have to spend all of our electrons. We don't have a choice. And fortunately for us, iodine is able to break the octet rule. So we're going to take those 2 electrons and we're going to give them to our central iodine, it'll also pick up a negative charge in the process. So in this example, this was an example where we used the fact that our central atom could break the octet rule to give it a lone pair, right? And an extra charge. In the previous one, we just gave it a lot of bonds. You just have to take it problem by problem to see what method you're going to roll with. Okay, so let's see. So we have to do this during the multiple choice problems before answering those. Are you talking about the about drawing the Lewis structures? I can. So Raj, actually, you do not have to draw Lewis structures during the multiple choice exam. Anytime you need a Lewis structure, I'll provide it for you. Structure in the Canvas exam. Yeah, you will only have to draw Lewis structures on the take home, but during the time constraint multiple choice, I give you the Lewis structure. You don't have to worry about it. Okay. Okay, Diana, you wanted to see, yeah, and yeah. All right, Diana, you wanted to see ICL. 4 negative, which I'm guessing, correct me if I'm wrong. Oops. You want to see this guy. ICL 4 with a negative charge. Okay, so here we have iodine, which comes in with 7 valence electrons. Chlorine also comes in, oh, that looks like a weird E. Chlorine also comes in with 7 valence electrons, but we have 4 of them. So 4 times 7 is 28. Heck yeah. Heck yeah. I am celebrating my Friday by writing a bunch of exams, but I'm actually planning on celebrating by watching. My kids and I started a new anime last night. The first episode was pretty cool, called Drifting Dragons. It's on Netflix. It was only available in Japan, but it recently licensed it to Netflix. So the first episode was pretty cool. Anyways, that's how I'm like, why did I start talking about anime? Because I'm talking about how I'm celebrating Friday. Hopefully you all have fun plans. Let's see. Oh, you noticed. Dude. It's the daily mixtape. My all-time favorite band. Which is, if you're wondering, the White Stripes, my all-time favorite band, did all their album art in black, white, and red. So I changed up the color scheme today. Oh, Diana, you do? We just started it. We just started it. We watched the first episode last night before the kids went to bed, and it was beautiful. Yeah, so I'm stoked. And it's, my wife can be kind of on the fence with anime, but she really liked it too, so it's kind of like something our whole family can enjoy, which is nice. Because when it comes to My Hero Academia, that's just the kids and I. My wife is like, why is everyone yelling all the time? Okay, anyways, let's let me get to this this prob. So totally. Okay, so we've got our electrons, right? Let's see. 28 plus 1 is 29, plus 7 is 36. 36 electrons to spend here. And I'm going to put iodine in the middle and attach all my chlorines. And this is going to take, oops, cancel. Uh, 2, 4, 6, 8. Leaving us with, oh, not 32. Holy moly. Math, am I right? 28. 28 electrons. Now, each chlorine needs 6 more to have a full octet. We have 4 of them. 4 times 6 is 24. So that'll leave us with 4 electrons in the budget. So let's complete all of our octets for chlorine by writing 24 dots. All right, now we have 4 electrons left to place. And fortunately for us, our central atom can break the octet rule. So we can give iodine 2 more lone pairs. It will pick up a formal charge of -1 when we do. And so this is the Lewis structure for, I actually don't even know the name of this polyatomic ion. ICl4 with a negative charge. Totally. So that is that dude. You'll notice that oh, let's see. Okay. So where is that? At which step? Why would you? Okay, sweet. Oh yeah, no worries. The lag actually I think was on my end. OBS temporarily disconnected. So the reason why we'd rather add lone pairs. So okay. So here's the thing. I'm gonna go to a new slide. All right. So here is a great question. For extra electrons, should we do double bonds or lone pairs? All right. This is an excellent question. And sometimes you'll go double bonds. Sometimes you'll go lone pairs. All right. But, which might make it sound confusing. But here's the cool thing. The guiding light for whether you go for double bonds or lone pairs. Oh! Yes. Okay. Okay. That'll be a... Okay. Here, hang on one second. Okay. So, double bonds versus lone pairs. If you look at the structure that I had drawn on the previous slide, which I'm, going to redraw here. So I had this drawn out. And then okay, versus we could take those extra electrons and instead use them to make double bonds. And Diana's first question is why did I do lone pairs as opposed to double bonds? And the answer is sometimes you'll roll with lone pairs. Sometimes lone pairs will be better. Sometimes double bonds will be better. It depends, and that may initially sound confusing, but here's the good news. What determines whether or not you go with lone pairs versus double bonds is you got to look at which one will allow you to have the smallest formal charge possible. All right? So whichever structure has minimal formal charge is the better resonance structure. So we should look at both, analyze them for their formal charges, and based on whichever one has the smallest amount of formal charge, that will be the best resonance structure. So if we look at in our first structure, all of our chlorines are the same. All right. When chlorine is neutral, it has 7 electrons. In this structure, it has 1 bond plus 6 electrons in lone pairs. So all of our chlorines have no formal charge. Now let's look at iodine. When iodine's neutral, it has 7 electrons. Now in this structure, it has 4 bonds, so that's 1 electron per bond, plus the 4 electrons it has in lone pairs. So 7 minus 8 is -1. So in this structure, we have 4 chlorines with a formal charge of 0, and an iodine with a formal charge of -1. Now, in the second structure, 2 of our chlorines, the single bonded chlorines, are the same as the chlorines in the first one, right? They have 7 valence electrons when they're neutral. They have 7 electrons in the structure, so they're 0. What changes? We see changes in the double bonded chlorines. And here's how. Chlorine, as we know, 7 electrons when it's neutral. Here it has 6 electrons in lone pairs, but then 2 bonds. So that 6 plus 2 is 8 each double bonded chlorine has a formal charge of -1. In addition, there's a change to the formal charge on iodine. When iodine's neutral, it has 7. In this structure, iodine has 6 bonds. 7 minus 6 is +1. So here, the iodine has a formal charge of +1, and the two chlorines have formal charges. The double bonded chlorines have formal charges of -1. So this right here is a better resonance structure. This is the best resonance structure because it has minimal formal charge. All right. So Diana, the answer to your first question, which was why can't we just use those extra electrons to make double bonds? You can, and in fact, that is a resonance structure of this molecule. But the question you have to ask is it the best resonance structure? So since when you use those 4 extra electrons to make 2 double bonds, you get a structure that has 3 formal charges in it, whereas when you use them to just pop lone pairs on your central atom, you only have 1 formal charge. That structure will be better because formal charge is minimized. All right, so you can do that, but weigh all your options and then look at your formal charges, and that will tell you whether it's best to have them as lone pairs or have them as double bonds. Again, it'll be different for each molecule. Sometimes double bonds are better, sometimes lone pairs are better, but what your guiding light to either of those opposite conclusions will be the same. Follow the formal charges. Whichever structure has the fewest formal charges will be the best. Assuming the octet rule is fine. Does that make sense? And if it doesn't, let me know because I can explain it a different way. If that's not quite clicking yet. Ah, okay, great question. Actually, okay. Another great question. Okay. Actually, the molecular... Okay. I totally see what you're going for. Because the one on the left has 4 atoms attached and 2 lone pairs, which is an octahedral electronic geometry. But then when you look at the other one, you're like, oh, those are 4 groups, so shouldn't that be tetrahedral? Okay. So we're bumping up against a part of the map that we're not supposed to be wandering in. You know that thing when you're playing a video game and you go to the edge of the map, but then there's nothing programmed beyond that and you can't get farther? We're bumping up against that part of Gen Chem. All right. Resonance structures have the same geometries, same hybridization. Doesn't change. and it looks like it is here. All right. So here's the deal. So first, to kind of get at your question, how are these two things resonance structures? Here's how they're resonance structures. So I'm going to draw the no double bonded system. And show you how you get to the system with two double bonds through resonance. All right, so I'm going to draw my two lone pairs on iodine here and here. So first, you can take this lone pair on iodine and use it to make a double bond with one of the chlorines. And again, drawing in all my lone pairs here. All right, we can take one of those lone pairs and use it to turn into a double bond with chlorine. The first structure, we had a formal negative on iodine. Now that'll sit on chlorine. And then you can take the other lone pair and use that to make a double bond between iodine and another chlorine. All right, so that's how they're... Totally. No, not at all. Never apologize for getting help. That's literally why I'm here. Okay, so this is how the resonance structures of each other, because we took the electrons that were on our iodine and used them to create multiple bonds to our chlorines. Totally. Okay. So that's what makes them resonance structures of each other. It's just because they are what's the word I'm looking for? It's just, we're just moving around electrons, right? We're not changing which atoms are attached to which atoms. That's all there is to it. All right. Now, if you switch gears for a second. So this is the best resonance structure, as we've already described or talked about. And here we have 4 atoms and 2 lone pairs, which gives us 6 electron groups. All right, 6 electron groups means that our electronic geometry is octahedral. And the fact that we're octahedral with 2 lone pairs means our molecular geometry is square planar. Yes, there is. Exactly. There is a pesky missing piece. Okay, and here's the deal. I'm about to show you what that missing piece is. And you're not going to get tested on this missing piece because the missing piece I'm about to show you is something from inorganic chemistry. This is a thing from an upper division chemistry class that doesn't belong in a general chemistry context. So the answer to this question, because it turns out the geometry is the same no matter what, and the geometry of this guy, as in green that I boxed, is square planar. Turns out the resonance structure is also square planar, even though it doesn't look like it. And the reasons why it's square planar is because of things that I'm going to use to describe this, but know that you're not going to get tested on it because it's beyond the scope of this course. Now, so I just told you that the guy boxed in green is square planar. The dude on the very right that I'm boxing in yellow is square planar as well. Not tetrahedral. And here's why. Let's look at the hybridization. Well, when you look at the hybridization for 6 electron groups, your hybridization is sp3d2, right? Because we have 6 groups, so we need 6 orbitals in the mix. It's sp3d2. And the double bonds, the pi bonds here are made with unhybridized whoa, things got sloppy there in Photoshop for a second. Unhybridized d orbitals. All right, so literally what's going on iodine in that resonance structure with 2 double bonds is we have a chlorine iodine. Oops, that's kind of ugly. Sigma bond that forms. All right, but then the pi bond between chlorine and iodine comes from an unhybridized p orbital on chlorine, and then, get this, this is where it gets, this is way beyond the scope of this course, but it's the answer to your question. An unhybridized d orbital on iodine. All right, and these two blur together to make a pi bond. Between chlorine and iodine. All right. So this right here is what's going on when we draw. Sorry, this chlorine has one more lone pair on it. All right, that's what's going on when you draw that chlorine double bonded to the iodine. Yes, Diana. Oops. That is what makes that resonance structure square planar. It's the fact that to make those double bonds, you're having to stay flat so that you can make the pi bond with an unhybridized p orbital and a d orbital on iodine. Yeah. Yeah. To be honest, this is upper division chem major stuff. This is upper division chem major stuff. There is zero chance I would test you on it. But it's the real explanation, or the real answer to your question. So give yourself a high five. You are thinking like a scientist. Okay, Vraj, sorry. Yeah, totally. All right, let's see. Vraj, I know you asked a question up here. Sigma and pi bonds. Okay, great question. Who? Where was that? Oh, there it is. Okay. Yeah, Raj, Sigma and Pi are only on the written exam. Totally. Totally. That's awesome. You can actually. You can. Yeah, I saved the Sigma and the Pi stuff for the written exam because a lot of it is drawing, and it's like, how do you test drawing with multiple choice? You can't really. You know what I'm saying? So I saved kind of the art class portion of the exam for the time you for the time when you actually are writing on the physical thing. Hey, it's not cheating if the test is open everything. Which I'm a firm believer that is the only way to give a take-home exam, because if you're worried that the only way to ensure that no one uses the internet is to give a test in a closed room where everyone's there and no one's on their phone, and you just can't do that. And it's not that I don't trust everyone, but I also just know human nature, because I was a student, and I know every time there was a take-home exam when the professor was like, you can use the book but not the internet, or you can just don't talk to anyone else in the class. It's like you get texts from people who are like, what are you getting for problem 3? You know what I'm saying? It's just gonna happen. So rather than make restrictions that penalize the most honest among us, I like just doing open season, use everything, use everyone, and I'll write the test accordingly. Plus, there's something about, I don't know, there's something I actually like about a collaborative test-taking environment, where you're writing something that's challenging to the point where you need other people to get there. I don't know. There's something about that I find appealing. Oh my gosh, I took it from you. You can't cheat on a test that's open everything. Oh, you're gonna have to try to wait for another class. Find another instructor that you can cheat on. That's awesome. Yep, it's real life. Yeah, yeah, exactly. Exactly. Shoot. You got a question? Then fire away. Yeah. Ah, will I write a... Oh, great question. Great question. So here is um, the answer is we will have to see. Um, we'll have to wait and see. This is in general my letter recommendation writing policy. So I only write letters for students who score a letter grade of A or higher. And so I don't know what your grade is off the top of my head, but it so whether or not I will write you a letter depends upon what letter you get at the end of the semester. So after the final and everything's graded and final grades are submitted, then shoot me an email, and we'll be in contact then. But whether or not I'm able to write you a letter, because that's just my yeah, totally that's just my letter writing policy. So if you get an A, I will totally write a letter. Totally, that's the way I roll. So, and again, I have no idea what anybody's grade is in this class off the top of my head, but so yeah, so we'll wait and see. It'll build suspense as the semester moves towards its end. Totally. Yeah, man. Yours have two. I have. I believe in you. I have full confidence in your abilities to succeed. And that is the truth. Oh, Diana, great question. It is not. We have one more next week. Yeah, we have one more next week. So the thing is, our last office hours of the semester is next Friday. So here, let me. And it falls, I think, at an opportune time. So our last office hours will be on the 15th. And this is by design. It will land after exam 3 closes. But it also lands before the final. So it'll give you an opportunity. You'll have all just turned in. Yep, exactly. Everyone will have just turned in their exam 3, so that'll be fresh in their head. So it'll give you an opportunity to talk to me about how you're doing. Tell me how much it sucked. Later, dude. Yeah, and office hours, you can tell me how much you didn't like the third exam. But also we can talk about the questions that you had trouble with. I'm more than willing to go over them, walk through any questions, the whole thing, all 3 versions of it if you want to. And then in addition, it'll give you a chance to ask questions about the final, kind of as you're gearing up for that, because that will be on Wednesday. So this Wednesday is exam 3, and then a week after exam 3 is the final exam. So, okay, totally. Dudes, thanks for coming out. You both rock. And if you're both exiting, I think that is where I'm going to call this office hours. Thanks to everybody who will be tuning in to watch later. Remember, we got one more next week after exam 3 before the final. We're diving into the last week of class. I will catch you all on Monday. Later.